Homework Solution 2.14. A 60 Hz power system is used to deliver electricity to a residential circuit. The load consumes 20 kVA at 0.92 power factor lagging when supplied at 120 volts RMS. The impedance of the line connecting the load to the voltage supply is 0.005 plus J 0.05 ohms. What's the magnitude of the supply voltage at the source end of the feeder? What is the power lost in the feeder? What size capacitor in both ohms and farads is necessary to improve the power factor to 0.95? To what value should the source voltage be adjusted in order to maintain the load voltage at 120 volts? And what is the new power loss in the feeder? So the given for this is again going to be a circuit diagram. We know that we've got a feeder, input into that feeder. We've got a line that connects the feeder to the load. That line has a resistive and an inductive component to it. The line itself has a resistance of 0.005, but there's two branches, the top branch and the bottom branch, so we'll combine those together into 0.01 ohms, and then we'll do the same with the series reactance. 0.05 plus 0.05 is just 0.1 ohms of inductive reactance. We've just got one load in this case, ZL, and we know that it is supplied at 120. And since that was the voltage given to us, we're going to go ahead and use that as the reference. It's not a very good Z right there. ZL. What do we know about this load? We know that the ZL is going to be equal to 20 kVA. So that's equal to the magnitude of the apparent power for the load. And we know that the power factor is equal to 0.92. We are asked to find a wide variety of things in this problem. What is Vs? What is the total power lost in the feeder? What is X? And C, sorry, not, yep, what is X and C for a power factor equals 0.95? What is Vs for new power factor? And what is P feeder once we've changed the power factor? So if you're curious about this, what happens is that if there's going to be we set the voltage of the, say this is a transformer or something, in a power system we'll set that voltage, and then there'll be a voltage drop across this element across the line due to the current draw by the load. So you have to increase the voltage end to get the appropriate load voltage here. If you increase the power factor, you decrease the current draw, therefore you decrease the voltage drop here. If you then don't decrease the feeder input end voltage, the supply voltage will go too high. And so when you power factor correct, you also have to decrease the input voltage to the feeder. And that's what this problem analyzes. So if we want to first determine the original voltage input to the feeder, the solution is that Vs here is going to be equal to the drop across this plus 120 angle 0. Vs equals V line plus V load. It's just a KVL. V line here is going to be equal to I line times Z line. So we can determine I line because we know some properties of the load right here. We know that S of the load is equal to I line complex conjugate, or I line star, times V load. I'm using I line there because the load current and the line current are the same thing. So just have to use this information here. And so I know S is equal to 20 e to the third at an angle of inverse cosine of 0.92. And we were told that this was a lagging circuit, so I don't have to mess with the minus sign there. And so if I combine this information, I find that I line is equal to 20 e to the third at an angle of inverse cosine of 0.92 divided by the voltage, which we know we were serving this load at 120 angle 0. And then whatever that answer is, I just take the complex conjugate of it, and that'll give me I line. Throw that into your handy dandy TI-89. You'll find out that the line current in this example is 166.67 at an angle of negative 23.07 amps. So I've got my line current there. And go ahead and plug it in right here to determine line voltage, the voltage drop across the feeder itself. And so that's going to be 166.67 at an angle of negative 23.07. Need to multiply that by the impedance of the feeder, which was 0.01 ohms plus J 0.1. You do that multiplication, you're going to get a voltage drop across the line of 16.75 at an angle of 61.22 degrees. So the answer to part A is the supply voltage, the original supply voltage, is going to be equal to the load voltage, which was 120 at angle 0 degrees, plus the 16.75 at an angle of 61.22 degrees. Should have my units there. Anyway, that gives me an input end voltage of 128.9, angle of 6.540 volts. And that's the input end to the feeder. That's the voltage. If I can scroll up, that's the voltage right here, Vs. So part B asks us to determine how much power is lost in the feeder. So this is the feeder model right here. It lumps together the forward connection and the reverse connection, and real power is only dissipated by this 0.01 ohm resistor. So to determine that power, I'm just going to use the formula that the power in the line is going to be equal to the magnitude of the line current squared times the resistance in the line itself. So that's just the line current, 166.67, times 0.01 ohms. And that gives me a power loss to heat of 277.79 watts of real power loss there. So part C here said what size capacitor in ohms and farads is necessary to improve the power factor to 0.95. So we'll scroll down. And so just so we're familiar with that, we've got our power triangle, and we know that this is given by this right here. I didn't calculate it before, but we know that the angle of the apparent power is always opposite to that of the current, so it's 23.07. So this angle here is 23.07 degrees. That means this is going to be, and this is 20 e to the third volt amps. So that means this is 20 cosine of 23.07, and this is 20 sine of 23.07. So if we were to write these down, this was 18,400.5 watts, and this is 7,837 var. So in power factor correction, what we're doing is we've got P stays constant, and we try to reduce Q. So this is Q old. And what we're trying to do is reduce the Q to a new value. The difference between Q old and Q new is the amount of capacitive Q we need to add to the system to perform the power factor correction. So in this case, we were given what the new power factor angle is. We were told that the new power factor angle is going to be from is 0.95, so that we can just determine the power factor angle from the inverse cosine of 0.95. So we get that value, which is 18.195 degrees. So we're going from 23.07 degrees down to a new angle of 18.195 degrees. So that's also going to change S. So to calculate what the new Q is, we have to know that the relationship between P and Q has to be given by this angle right here. And what's the relationship in that right triangle between the opposite and the adjacent? Well, that's given by the tangent. So the tangent of phi is opposite, which is Q nu over P. So that's just tangent of that right triangle right there. And so I can determine the new Q from the old P times the tangent of the power factor angle that I just calculated right there. Right, that's the new power factor angle. So Q nu is going to be equal to 18,400.5 times the tangent of 18.195 degrees. And so I get a new Q of 2575.93. And that's in VARs. So previously I had 7,837. Now if I correct the power factor to 0.95, that means I only have 2,575.93 VARs. So from this figure, we recall that Q old plus QC equals Q new. So that allows us to determine QC. It's equal to Q new minus Q old. And so that is 2,575.93 minus 7,837. That's this value here minus this value here. And that gives me negative 5,261.07 VAR. So that's good. I got a negative sign on it. That means it is capacitive, which we know needs to be the case for power factor correction. So that's good. So that's the amount of QC we need. Just to summarize, minus 5,261.07 VAR. Now I need to convert that over to a capacitive reactance, and I'm going to use the fact that in this circuit the capacitor is going to be added in, way up there. Capacitor for power factor correction gets added in parallel, which means it's also going to have 120 degrees across its terminals. That's pretty much always the case. So I'm going to use the equation for Q sub C when I know the voltage across a purely reactive element, and that's the magnitude of the voltage across the terminals of the capacitor divided by X sub C. So I can rearrange that as X sub C is equal to the magnitude of the sending end voltage divided by Q sub C. And so that is 120 squared divided by this value, 5,261.07. And that gives me 2.73709 ohms is equal to the amount of capacitive reactance that I need to achieve that power factor correction. To convert that over into farads, I need to use the fact that X sub C is equal to 1 over omega times the capacitance, which says that capacitance is equal to 1 over omega times X sub C. So that's going to be equal to 1 over 2 pi times 60 hertz times 2.73709 ohms. And I'm going to get a value of 969.127 microfarads equals the value of the capacitor that I want to put in there to correct the power to power factor to 0.95. So part D asked us to determine, if we scroll all the way up to the top, part D asked us to determine what value should the source voltage be adjusted in order to maintain the load voltage at 120. The problem with putting that power factor correction capacitor in there is it's not enough. If we correct the power factor, that's going to reduce the supply current and therefore reduce the voltage drop, and it's going to raise the load voltage. So we got to repeat this calculation here, given our new information. So in part D, we say that the new power triangle is going to be equal to the old power, because we didn't change real power, so that's 18,400.5 watts. We do have a new Q that came from this value right here, 2,575.93. Remember, that's our calculation for the new Q when we did the power factor correction right here. So we do that, and we get a apparent power of 18,579.9 at an angle of 7.970 volt amps. So that is our new power absorbed by the load. We can determine the line current that's now being drawn by the load the same way we did before. We've got the line current equals S over V quantity starred. So we've got 18,579.9 at an angle of 7.970 divided by 120 at angle 0. We want to maintain the load voltage at 120 degrees. We've got this new power triangle. The real power stayed constant, but we've got a reduced reactive power. And so we get a reduced line current of 154.83 at an angle of negative 7.97 degrees amps. So I want to just quickly compare that to our old calculation. We see that our line current was 166.7 amps. We've gone down all the way to 150 amps. So indeed, power factor correction decreased the line voltage, decreased the line current, and therefore the voltage drop across the distribution feeder. Our new supply voltage to main 120 volts at the load is going to be 120 angle 0 degrees plus the voltage drop across the line, which is just the current through the line, 154.83 at an angle of negative 7.97. So that's that current now flowing, just to remind you, flowing through those two elements right there. We need to multiply that by that impedance of the feeder, 0.01 plus J 0.1. And we get a new supply voltage of 124.6 at an angle of 6.97 degrees volts. So we have to reduce the voltage to the input end of the feeder down from its previous value down to 124.6, and its previous value was 128.9. So a little bit of significant reduction there. There is some power savings here. Part E asked us to calculate the new power dissipated in the line. We know that the real power dissipated in the line Again, it's just the magnitude of I squared times the resistance in the line. The line resistance hasn't changed, it's still 0.01 ohms, but we decreased this current as we just indicated. So that's 124.6. Sorry, not 124.6, that's voltage. 154.83. Square that, because it's I squared R, multiply it by 0.01, and you get 239.733 watts is the new line power. So we have decreased the amount of power that's wasted in the line. The old value was 277.8 watts. Now we're at 239.7 watts. So we did indeed reduce the amount of power lost in the distribution feeder.